The purpose of lab number 2 is to analyze the movement of a falling object. Tracker is utilized to obtain information about the position of the object with relation to time. In order for Tracker to gather accurate information, it is important to create an axis, and I chose my object as the origin, which means the object's velocity will be in the negative y direction. Also, it is important to provide Tracker with the length of my chosen object, so there is a reference for the distance traveled. I chose a notebook as my object with a mass of 0.21 kilograms and a length of 0.25 meters. After the data is collected from Tracker, it is clear the notebook accelerates as time goes on due to the fact that the slope gets steeper. This means that Fnet is not equal to 0 in this scenario because magnitude of velocity does not remain constant. In order to investigate the forces present in this scenario, a computational model was created that replicated the motion of the notebook. Before creating this code, it is important to identify the fundamental principles of this lab. The momentum principle is crucial to this lab because it can be derived to calculate the velocity and position update formulas. Again, in this scenario, Fnet is in the negative y direction. The first code considers only the force of gravity. The crucial values that must be entered are the mass of the object, which is 0.21 kilograms, the initial position and velocity of the object, the time interval, and the force of gravity. The initial velocity of the notebook was 0 due to the fact it starts at rest. The force of gravity is simply 9.8 meters per second squared times the mass of the object. The time interval is less than 0.567 seconds because this was the final time interval produced by Tracker. After such values are entered, the updated velocity and position formulas are calculated within the while loop. This output of the code is accurate to the real-life scenario due to the fact that the slope gets steeper as time progresses. However, it will be useful later on to compare the data points collected from Tracker to the data points produced by the code to see if it is okay to only consider the force of gravity. Before doing so, a second computer code was created that accounts for the effects of gravity and turbulent drag. The process is very similar to the prior code, except in this code, Fnet is equal to the force of gravity plus the force of turbulent drag. In order to calculate the proportionality constant, I simply used trial and error until my final data point was extremely close to the final point collected from Tracker. Similarly to the output of the computer code considering only gravity, this output has a slope that gets steeper as time progresses, proving again that Fnet is non-zero in this case. This time displacement graph compares the actual y position, which was collected from Tracker, to the predicted y position when only gravity is present, and the predicted y position when gravity and turbulent drag are accounted for. In this graph, it is clear that the computer code considering gravity alone will overpredict how far the notebook actually falls. This is due to the fact that turbulent drag is actually present in the real-life scenario, which causes the object to not fall as far. Clearly, the code that takes account for turbulent drag is more accurate to the real-life scenario because the final data is closer to the one collected from Tracker. When considering terminal velocity, it is important to take into consideration turbulent drag. This is because terminal velocity is reached when the force of the drag is proportional to the velocity of the notebook. Therefore, it is quite important that the force of turbulent drag is considered when analyzing the terminal velocity. If the object was thrown downward rather than dropped from rest, the terminal velocity would still remain the same. In order to investigate this fact further, I manipulated my computer code in order to calculate the terminal velocity. First, I made the initial velocity 0 meters per second, and the output produces the terminal velocity with respect to time. As seen in this output, the terminal velocity is 4.13 meters per second. Next, I changed the initial velocity to 1 meters per second in the negative y direction. The output is the same as when the initial velocity was 0, proving that the terminal velocity of an object is not dependent on the initial velocity.